Okay, so we now know how to deal with a system that is either at equilibrium, we can solve for K, or we can even ask the question, is it at equilibrium? Check the Q, see if it's too big or little. And if it's not at equilibrium, we can now calculate what the concentrations will be at equilibrium, all right? So we've dealt with all the various mathematical scenarios. What I want to talk about now is an equilibrium system that is at equilibrium, and then we're going to do something to it. We're going to add some stuff to it. We're going to poke it. We're going to stress it, right? The number one rule of babysitting and parenting, all right, and teaching, is let sleeping babies lie, right? If they're sleeping and they're supposed to eat, oh, they're supposed to eat, but they're sleeping. Let them sleep. In terms of students, when they're working quietly, let them work quietly. Don't disturb them. What we're going to do today with an equilibrium system is the total opposite to that. We're going to take an equilibrium system, and we're not going to let it sit and let it lie quietly. We're going to poke it. We're going to stress it. And we're not actually going to poke it. You can't actually just poke an equilibrium system. That's with the analogy of the baby. If you wanted the baby to wake up, you could poke it. I got into trouble for stuff like that. Anyway. So we're going to stress the equilibrium system, and we're going to ask what's going to happen to that equilibrium, all right? We're going to apply stresses to the equilibrium system. And that's the term that we use. We use the term stress. Even though the equilibrium system doesn't have little eyes and ears and brains, we still use the term stress. I'm entertained by that. An equilibrium system under stress. Again, this particular principle named after someone, obviously someone who had tested this and made some observations. These tests and observations would have been done before the knowledge of an equilibrium constant, right? Before the calculations. Way back then, when they first discovered this idea, they called this constant the law of mass action, because it had to do with the way you could look at an equilibrium system and how much material you'd get out of the reactants or the products. That was before they even realized it was a truly equilibrium system. Once the theory or the idea of an equilibrium system was proposed, then the equilibrium constant, or this law of mass action constant, became quite obvious what it was doing. It was this relationship between the reactants and products. So the name would have changed to an equilibrium constant. And LeChatelier would be studying equilibrium systems as well. He would set up an experiment, I would assume, of some sort that would allow to go to equilibrium, and then he would have applied a stress to that equilibrium. He would have done something to it. In terms of what a stress is to an equilibrium system, if you change the concentration of the reactants or products, so add some more reactant, or remove some of the reactant, or add some product or remove the product. Another stress on an equilibrium system is change the temperature of the system. Heat it up, cool it down. And another way that you can stress an equilibrium system is to change the volume of a gaseous system. And that's because by changing the volume, you're changing the pressures, and really pressure is another measurement of concentration. Right, actually, right now is not a bad little time to mention that to you. This is not something that you need to know in order to have success in this unit, but you will encounter it in university. You'll notice in all of our equilibrium problems that it's either aqueous or it's gaseous. Actually, for most of them, they've been gases. And we've been talking about these things as being concentrations, right? Concentrations in moles per liter. And when you're talking about a gas, you don't usually talk about a gas in a concentration of moles per liter, but really the pressure of a gas is a representation of concentration, all right? If you have something that's highly concentrated in a beaker, it means that you have a lot of the molecules or ions, whatever you're dealing with, a lot of those molecules and ions in a very small volume. In other words, you've jammed them in, right? A concentration measurement is almost like a number density. It's not a mass density, but it's a density of how many particles are in a particular volume. So if you've got a highly concentrated substance, you've got a lot of those little things in that little volume. And the pressure of a gas is really the same thing. If you have a gas, and we'll just put it in a balloon for no reason, and you have it in there at high pressure, then it means that you've got a lot of particles in that balloon for a particular volume. Now those particles aren't necessarily dissolved in anything, but again, it's a number density, a lot of particles per volume. And we can actually see that representation through our good old PV equals nRT. Oh, we haven't seen that for a while, so we'll look at that again. If you take a look at PV equals nRT, and you have it at a constant temperature, so if the temperature is constant, then R and T are constant, all right? And if R and T are constant, then we can see here, if we say these are constant, we can see here that P times V is proportional to N. P times V is, well, it's equal to N times some constant K. We'll just make that into a big constant K, those two there. And we know that C equals N over V, right? And I can bring that V down here. I can have P equals NK over V, all right? And I could then bring that constant to this side. The pressure divided by some constant that's determined by the temperature is equal to N over V. And N over V is our concentration unit, which means pressure divided by a certain constant will actually convert directly into moles per liter. So a pressure is actually another way of describing concentration of a gas. And that's why we can use it in the equilibrium scenario, because equilibrium is only dependent on concentration, not on pure numbers of moles. Okay, so let's talk about how we can stress a system. Let me just describe this to you for a moment before you get writing so you can make some sense out of it. The first effect we want to look at is changing the concentration. Next, we're going to look at temperature, just like in our list, and then we're going to talk about volume of a gas. So here's what we're doing. In my first example, I've got an A in equilibrium with B, and I want to stress it. And the stress is that I'm going to add a bunch of A to the system. So if I'm talking about a beaker with some A and B in it, I'm going to take maybe a solid chunk of A, and I'm going to add it in there, and it's going to dissolve. And now I've really increased the concentration of A by adding A to the reaction vessel, okay? If I'm talking about a gas, maybe this wasn't a balloon and it was some kind of a piston of some sort, if it didn't pop the balloon, I could maybe use a syringe and I could inject some of A into the balloon and make the concentration of A go up. And the response. LeChateliers Principle states, and actually I jumped right over that, it states that the equilibrium will respond to the stress by shifting in the direction that opposes the change in order to return the state back to equilibrium. So whatever you do, the system will shift to try to get rid of what you did, right? And I've heard many teachers say, I guess that's kind of like human beings, right? If you've got a stress, then you'll move away from the stress so that you can have less stress. You know, I don't know. I'm always kind of like, what? Huh? I suppose that's true, right? Like if, I don't know, if let's say I'm working in the lab and I spill something and it starts on fire, that might cause me some stress. I'm not going to stick around. I'd likely move away from that stress. I don't know, it's kind of a silly thing. I could never get into that particular explanation. So here we've got a stress, we've added A. The response is to do the opposite of what has happened, and it shifts to use up the excess A. The equilibrium moves to use up the excess A, and then I've got a blank for the shift, just so that we can have it a little participatory here, so you guys can think about what goes in the blank. I was evaluated yesterday. I feel like an invigorated new teacher. No effect. If it's going to shift to take care of this increased A, which direction is this equilibrium going to shift? And this is not rocket science. It is straightforward. Yep. It's going to shift right. So this is going to shift right. We can even think of it in terms of a calculation of Q. If I add A, if I add reactant, then that means I'm putting a bigger number in the bottom of our equilibrium expression law. That's going to make the number smaller. The Q is going to become too small, and it shifts right to produce more product, to bring the K back up, or bring the Q back up until it's equal to K. So we have actually already encountered this situation when we talked about, is it at equilibrium, and the calculation of Q. In actual fact, the textbook talks about this before they even talk about the value of Q. But I'm mathematical. I like to have the math first, so then I can think of it in terms of the math. You don't have to think of this in terms of the math. It's a pretty straightforward thing. You can think of it in terms of, we increase the A, and there's too much A. It's going to have a stress. It's going to try to use up the A. It's going to shift right. That's great. That's a great interpretation of it. But mathematically speaking, you make the A big. Again, remember, reactant is on the bottom. Product is on the top. As soon as you add A, this gets big. We've kicked it out of equilibrium. It's not at equilibrium anymore. We've turned it into a Q, and the Q becomes tiny because we've made the bottom bigger. And if the Q is small, we know that it's going to react in such a way to bring it back up to be equal to the value of K. It shifts right to make more product. So if you like the math, you can link this idea to the math. You really can also just think of it in terms of the equilibrium having a little brain and saying, ooh, too much A. I better shift to the right and make more product, right? All right. Now notice, once equilibrium has been reestablished, A is a little higher. Even though it tried to get rid of some of the A, it couldn't get rid of it all, because in the end, we've got a new two numbers in our equation, and because the bottom number became bigger, and as it shifts to make the product, it's gonna get to a new balance point that both of them are now higher. You've added molecules to the system. So A will be slightly higher, and B will also be higher because it's produced some B. No effect on the K. Now what I have next, and you can just put this underneath it, I just want to draw a little sketch to represent this, and it's not supposed to be in great detail, but essentially, again, I just want to do a little graph to represent, right, and I've got time and I've got concentrations. And we will make, and it doesn't really make any difference, I will put here that can be A, and that can be B. So we've got here B, and we've got here A. And right at this point in time here, A shot up. We've added some to it. So A gets shot up. We've added it to it. And in the end, it tries to turn that A into B. It creates a new equilibrium system. It can't get rid of all of A. And here B starts to rise up and we have a new equilibrium situation for B. And I apologize for those extra little marks on there. What will be true is that ratio of A to B before the stress will be equal to that ratio of A to B after the stress, because the K is constant. So if we were to take, again, B over A, they would end up being the same. On my graph, it doesn't look like that's the case. I didn't draw it perfectly to scale, but that would be true. I am a fan of putting a little grid on a test and saying, draw me a little sketch of what that would look like, that particular stress. So just be aware of that. Okay? And maybe just as an add-on here, K is constant. That ratio will be the same before and after. All right, let's look at another one just to get us kind of in the groove. So this time, instead of adding A, we injected some B, or perhaps dumped a solid chunk of B. To get you to think in terms of a response, it's the opposite. Increase B, it's going to shift to use up excess B. And you guys are a bright group, so you're going to know that which way is going to shift. In order to take that up, yep. It's going to shift left. And B will be slightly higher and A will be higher. I even have another example, and that would, I know from you guys, elicit some eye rolls. Really? Another example? It's killing us. I will just orally go over the next example. You don't need to write it down. Oh, some of you aren't even writing this one down, probably. That's what the giggling is back there. Opposite of previous example. She's right. Now again, I was going to draw a little sketch to represent this, but what I think I'll do is I'll jump down to that third example as well. We don't need to write it down, but I do want to just discuss it. Then I'll go back and we'll draw a little sketch of this stress with the other stress on it, just so that we can see it graphically. All right? So very straightforward. I've added some extra B. It shifts to the left. Because I've added more molecules to the system, I can't get rid of all of the B I've added. So after it tries to convert it back to A, there'll still be some extra B left, but A will obviously be higher. The K hasn't changed. It's the exact same situation except we're coming at it from the product side, all right? Now, before I draw the graph, let me just jump ahead to the next example, which I don't think you need to write. But it's simply a removal of a reactant or product, but the concept is exactly the same. So I'm going to jump ahead here. So don't write this down. I think we get the idea. But if we were to say decrease B, let's say we had A and B in this particular beaker, and I added something like C that formed a precipitate with B. In other words, it grabbed it up and made it into a solid at the bottom. In other words, it's not aqueous anymore. So if I then added C, and now I've got some BC all in solid at the bottom. In other words, I've removed some of the B by forming a precipitate of it, which that's one way you can actually remove something from a solution. So B is now very low. So what's the stress? Decrease B. So what's the response? Well, if you've decreased B, let's shift to produce some more B again. Okay? Which means if we decrease B, which way is this guy going to shift? It's going to shift. So somebody mumbled it somewhere. Right? It's going to shift right. It's going to shift right. Now, because we've removed some of the actual substance, you don't get it all back. Right? B becomes slightly lower because it tries to produce more of the B, and A is also lower because it's shifted over to the right. Because you can't recoup all of the B that you remove. Again, no effect on the K. So let's just draw a little sketch one more time to illustrate both of these. We can put them both on the same graph. And if pictures are truly worth 1,000 words, then we've gained lots of words without writing that particular slide. So again, concentration, time, and again, we're going to go with A as the blue, and I'll just have it end up over there. So there's A, and then we will go with, again, B as the red, and I'll have it end up on this line here. And it doesn't matter where it ends up, folks, on your sketch, as long as it ends up at equilibrium at some point. And what was that first one that I wanted to illustrate? I wanted to illustrate the addition of B, right? It was the addition of B. That was the one that we wrote. So in this case, in my graph, what do I have to do with the B line? Guiding you to drawing it correctly on the test. What am I doing with the B line? It's going to spike up. So addition of B, I'll have it spike up by 2. It's going to shift to produce more A, right? Which means this is going to come back down. It's not going to quite make it back to where it ended up. And I'll have that end at a certain square so that I can do the next addition. And then this one is going to increase up like this. And it's going to end up like that. And I've probably got it increasing a little too high, but it's not bad. And it won't dip back down. That's a bad drawing right there. It doesn't dip back down. It's nice and horizontal there. Okay? So this was illustrating, right, add B. Okay? And what did it do? It shifted right. Now, in that last one, what was the thing that we did? We removed some B, didn't we? We did a removal of B. So in that case, what happens? Well, if you do a removal of B, this is going to drop down. We'll have it drop down a significant amount. Doesn't matter how much we remove of B. I'm going to just put the reaction here, A, B, so we can visualize it. I've removed B. What's going to happen? What's going to happen to my B line? I've removed B. What's the concentration of B going to do in response to that removal of B? Yep, Ben? Sorry? Produce more. So what should happen to my curve here of my B line? Yep, Ben? It should go back up a little bit, and it'll never go back to where it was, but it'll go up a little bit. Like that. And what happens to the A in response to that removal of B as it shifts? What happens to the A? Yep. So it's going to dip back down. Get smaller. So it's going to dip down here somewhere. And is it going to dip below here? It depends on how much we removed. And I'm not really that worried about that type of thing. What I'm worried about is that you're making things bend and curve the right way. Okay? So this is remove B. Remove B. And again, K is constant. In every one of these, if I were to draw it to scale, that ratio of A to B should be the same after the end of each of these shifts. It's probably not the case in my sketch, hence it's a sketch. All right, we're okay with that? So adding and removing reactant product, pretty straightforward business. Let's now talk about, let's just do this orally. I want to get to the end of this. I'm sensing that you guys are like, yeah, this is making sense. Let's keep rolling. So let's not write this down. Here we've got a reaction here. If I then add CO2, which way is it going to shift? Right. We're okay, it's going to shift right. This is, okay. And if I then decrease CO, which way is it going to shift? If I decrease CO, oh, we gotcha. We gotcha. If I decrease CO, this is going down. I've removed it. It's going to shift right to bring the CO back up. It always shifts so that it does the opposite of what the stress was. If the stress was to decrease CO, then the response is to do something to increase the CO. And in this case, it's got to shift right to produce more CO. So this is definitely a right. If we increase CO2, it's going to shift to get rid of the CO2. Right as well. Okay. Let's now talk about temperature systems. What happens when the temperature changes? Now, I've already mentioned this a couple of times, and I'll say it again. You guys might already have this in your mind somewhere. But, well, I'll ask you, why do I always give you the temperature when we're doing an equilibrium problem? Why do I always have to write down that the temperature is this? Yep, Shauna? Yeah, because K is constant at a certain temperature. When the temperature changes, the K value changes. It literally changes the rates of the forward and reverse reactions, and it changes them at different amounts. It's an entropy versus enthalpy thing. Right? Because remember, these reactions are reversible, and one of them is going to be driven by entropy, and one's going to be driven by enthalpy. And entropy is very much energy related. Enthalpy is energy. So when you start changing temperatures, you start changing the energy amounts that are available for the reactants and products. It actually increases the amount of energy available for the collisions of the reactants and products. You have more effective collisions, right? You take away some temperature, or you decrease the temperature. I guess you can't take away temperature. That's kind of a funny idea. But you decrease the temperature and you've taken away some energy. So when you think of LeChateliers Principle and changing temperature, think about changing energy amounts that are available. When you cool something down, you need to imagine we're removing energy that is available to those reactant and product molecules. They'll be moving slowly. They'll have less energy available. When you increase the temperature, you're adding energy that is available. So when we talk temperature change, think energy available. Think that you're removing or adding energy. And if you do that, it becomes very easy, because if we then put the energy in the chemical equation, like we know how, we can just simply have it shifting to remove or add energy. So, first, an endothermic reaction. Because obviously there are two scenarios we can have, endothermic and exothermic, that deal with energy. And as we know, we can write a thermochemical equation that has energy in the equation, and if it's endothermic, it's a reactant, right? So all we're doing here is representing we're representing a thermochemical equation with energy as a reactant. And then, if you treat energy like it's a reactant or a product, it becomes the same as our last examples. And I'm hoping you can fill in the blank. If we've got energy on the left, and we increase the temperature, it means we have excess energy available to the reactants and the products, but it doesn't matter. But we've got excess energy available. It's like now there's too much energy. The reaction will shift to absorb that energy. Which way is this A going to shift to take care of this excess energy on the left? Which way is this thing going to shift? Yes. It's going to shift right. Okay? Blue. I don't like blue. Hard to see. Decrease in temperature, if it's endothermic. Take the temperature away, it's like you're taking the energy away that's available for that chemical reaction. It's going to shift to respond to this decrease in energy. It's going to attempt to produce more energy. It's going to shift left. And in this case, the K value does change. So treat energy as if it's a reactant for endothermic reactions, and then treat temperature as if it's an energy source, and you'll be able to get the shift very straightforward. Next, I have a graph again. I'm going to just quickly sketch these. So again, for those who like to see graphs, this will make things a little clearer. We're good to go? Good to go? So again, quick sketch. Again, you guys are just sketching too. It's not a big deal. Concentration, time. And again, we'll have our A and B. So we've got A coming down to here, and we've got B moving up to here, whatever colors you're using. Oops, that's an A. And what did we do for the first one? We increased the temperature, right? We had an increase in temperature. So I'll write that down here. So at this point, we're going to increase temperature. And this was endothermic. We're still under endothermic, correct? And so which way did it shift? It shifted right. So more A had to become B. As it shifts right, it takes A and turns it into B, which means what's going to happen to my A value as it shifts right? What's going to happen to the value of A as it shifts right? It's going to decrease a little bit. It's going to decrease a little bit. There we go. And I'll bring that down maybe to there. Excellent. And what happens to B as it shifts right? Yep, Jess? No, because I have not added any reactant or product. I haven't changed the concentration of A, nor have I changed the concentration of B by changing the temperature. I have not added any A or B. I've just changed the temperature. So there is no spike on this. All right? What happens to B as we shift to the right? What's going to happen to the amount of B as we shift to the right? Yep. It's going to get greater because we're shifting right. It's going to shift to the products. Now notice, this is the first time where instead of after the spike, they both moved up or both moved down. Here, they've come closer together, which means the ratio that I had here for reactant and product is different than the ratio that I have here. I've literally changed the ratio of reactant to product. That's a different K. We can even talk about what happened to the K. In this case, what happened to the K? Remember, K is product over reactant. What happened to the K in this case? Product over reactant. Yep. It increased. My product went up and my reactant went down. This is an increase in K right here. K increased at that point. Let's now talk about a decrease in temperature. We'll start from these exact spots. It's okay, we can continue on. So when you decrease temperature, which way does it shift? Yep, left. We're saying the same thing over and over again. Shifts left. So what's going to happen then to my A if it shifts left? What happens to the A concentration? Yep, it increases here. We'll make it get really hot or something. We'll really increase it. And what happens to the B as we shift left? Saying the same thing over and over again, but I want to hear it. It gets smaller, it decreases. Because I made such a big change, I'll make this one big here. All right. Again, notice that ratio has changed greatly. I now have much less product and much more reactant. What happened to the value of K in this case? It decreased. K went down. Because I haven't added any reactant or product, I don't have the spike. I just have a shift in this case. Just a shift. And that means that the K value becomes new. Concerns? All right, next slide is going to be exothermic. Again, it is the exact opposite. I would write this slide down because it's the whole thing flipped on its head, but it's still important. Increased temperature, too much energy on the right. Which way does this shift? Lexine, which way is this thing going to shift here? Lots of energy here. It's going to shift left. Left. Push it back that way. Decrease in temperature on this side. Which way is going to shift? Yeah, right. I do want to draw another graph. Again, you might think, oh, we just did that. But I want to stress to you that an increase in temperature for an endothermic reaction will result in a different K change than an increase in temperature for an exothermic reaction. It changes the K differently. So you have to think of like 4 things: endo versus exo, and increase versus decrease. And there's all these 4 different combinations, so I want to stress it. You might think it's a little overkill. Okay, who's kidding who? Jess probably thinks it's overkill, but I don't care. So again, I just want to make sure that we see that there is a difference. Concentration, time, you're getting the idea. I'm assuming you're all going to start at the same spots because that's what I've been doing. A versus B. I really don't care where the lines end up. Again, we know that that's B and that's A. And what did we do in the first one? We increased the temperature again, right? Increased the temperature. I didn't write on my last sketch that it was endo, but it's underneath the endo part of the note, I'm hoping. I'm hoping you've linked it to it. So this is exo. And if this is exo, then what did we determine, right? We've got A to produce, B, and what is it? It's plus energy, right? Energy. So we are increasing the temp. Which way are we shifting? Left. So what's happening to my A? It's going to go up a little bit. And what's happening to the B? It's going to go down. And what has happened to the K value? What did the K value do? I increased my reactants and I decreased my products. What does the K do? It decreases the K. And you will find that for an increase in temperature under endo, we'll do the opposite to the K. That makes sense, right? Because you're causing it to shift the other way. But that's what I wanted to clarify here, that you've got to be careful, that you got to think endo versus exo, increase in temperature versus decrease in temperature, and therefore increase in K versus decrease in K. Instead of memorizing it all, you should be able to just use LeChateliers Principle to get the shift, and you know how to calculate K, so you should be able to get the K, right? It's actually not too complicated unless you try to memorize it. If you memorize it, it might be tricky. So here we're going to have a decrease in temperature, and we're going to shift right. And so what's the A going to do? Yep. This is going to decrease. Again, I'll just bring it down to a certain value, whatever it is. And the A is going to decrease. The B is going to increase. We'll bring it up to there. Again, we've now changed that ratio. We now have more product and less reactant. We've made the top bigger, and therefore we've increased the K. I'm going to finish that with an okay. Okay? Okay. All right. Now, to talk about, we're not going to do the example. Changes in volume and pressure. These relationships I actually expressed on the board before we even started. And maybe I'll just write them down again. Miranda heard it, but wouldn't be able to see it. PV equals nRT, all right? If I want to relate the pressure to a volume, I can say pressure is then equal to N and then RT over V, right? And what I did on the board is I said, well, essentially, if that's constant, if we're at a constant temperature, constant, then you can see there that pressure is directly related to concentration, but the volume of a gas, the smaller the volume, the higher the concentration, and the higher the pressure of the gas. In other words, volume and pressure are also inversely related to each other. That's what this statement says. The smaller the volume, the higher the concentration of the gas, and the higher the pressure of the gas. In other words, pressure is inversely proportional to the volume. So if I were to take a syringe like this, all right, I can draw some air into it. I can close the valve. I can try to close the valve. I'm failing at closing the valve. What is wrong with this thing? It is faulty. Oh, it's close the valve this way. I can close the valve. Okay. Open it up. Close the valve. If I squeeze down on that, there's obviously going to be a higher pressure in there. You can see I'm straining. My poor little thumb is quivering with the amount of effort that I need to put on it to keep this syringe squished. And that's because there's a lot of pressure in there. As I decrease the volume, the pressure increases. I think we're okay with that relationship, right? That's essentially Boyle's law, right? Decrease the volume, increase the pressure. That's the inverse of the pressure. So that's essentially Boyle's law. Okay, now we're going to use this. And yeah, this is a wordy note, folks, and I still got quite a bit to go. I'm looking at my time. It's exciting. The lab isn't as long as a full period, so it might turn out that I got to finish the note before we do the lab, but whatever. We'll keep trucking. The concepts aren't complicated. I don't believe we've discussed anything that is that is completely blowing the mind of anyone in here. But in order to express it clearly so that you can go back in your notes and understand it, it's wordy. The way it is. Again, the system is going to respond to try to mitigate the stress, to decrease that stress. Pressure is related to the number of gas particles. And if you think back to the end of last year when we talked about Avogadro's hypothesis and things like the ideal gas law, you'll recall that I stressed nowhere in the ideal gas law does it state the identity of the particles. It has nothing to do with whether it's an oxygen molecule or a nitrogen molecule or some water vapor molecules or some carbon dioxide molecules. Pressure is determined simply by the number of molecules in a particular volume. And so when you increase the pressure, the system is simply going to try to decrease the number of molecules. Because an increase in pressure, in terms of the system, if it had a little brain and could reason, an increase in pressure would cause the system to say, oh, there's too many molecules in this particular space. I'm going to shift to the side that has the least number of gas molecules to kind of gather up as many gas molecules and bring that pressure back down. And if you cause the volume to increase, in other words, if I draw some of the air out, the system's going to say, whoa, the pressure's way too low around me. As a chemical reaction, I'm going to shift to produce as many particles as I can to bring the pressure back up to where it was. So it's going to shift to either get rid of gas particles or to increase gas particles, depending on what the stress was. Graphically, this is difficult to kind of express because what you're essentially doing is, when you change the volume, you're changing the concentration of both. You're either bringing them both up by increasing the pressure, or you're bringing them both down as a spike, right? The spike's going to bring them both down. Now, what that does is it disrupts the balance of the K value, and then you get an equilibrium shift to bring everything back into order. But it's dependent on where the gas particles are in the formula. It's dependent on, do I have more gas particles as reactants or more gas particles as products? So I can't just draw a standard graph for it because every one would be dependent on the specific gas particles in the formulas. So I'm not going to draw a general equation because it would be more confusing than clear. So let's just do this as some examples, all right? E.g., boom, there's an example right there. So here we've got a situation where we've got N2O4, one gas molecule here, and two NO2s. So this broke down into two separate gas molecules. Again, pressure of a gas doesn't care about the identity of the molecules. Doesn't matter whether they're big or small. So the fact that this is made up of two separate particles, even though they're half the size of this, it doesn't matter. That will exert twice the pressure than this, because there's two particles there. So if we then cause a stress like decrease the volume of the container. So here's a type of question. There's your reaction. I'm saying we've decreased the volume of the container, and I'm asking you, which way is it going to shift? So in my mind, when I get a question like that, I even think of my little syringe here. Decrease the volume of the container. I imagine I'm applying some stress to this. What's that do to the pressure? It increases the pressure. The system's going to say, oh no, too much pressure, too many gas particles. It's going to shift to get rid of some of the gas particles. Which side is it going to shift to? Which side has the least number of gas particles? Yeah, Kristen? It's going to shift left. Okay? I even imagine it, instead of shifting to produce less gas particles, I imagine it as if the pressure is literally squeezing the two particles together to form the one. That's what I've done in my mind. Is that what's really happening? I'm really not sure. But I imagine it as when I close this pressure down, I'm imagining, oh, those two are being squeezed together into one. Either way, it doesn't make any difference how you interpret it. Increased pressure, too many particles around, it's going to shift left to decrease those particles. Response. Oh, now I got to write this down. Oh, that's exciting. Response. Sorry, what was the response? We had an increase in pressure. The response is to decrease the pressure of the system to decrease the pressure of the system, it's going to go to the fewest particles, so it's going to shift left, fewest gas particles. Now, once equilibrium has been reestablished, you know what? I'm not even going to worry about that here, and I'll tell you why. It's hard to tell exactly what each of the concentrations are going to do because you're literally changing the volume. Both concentrations will spike up. You'll never get the concentrations to go back below they were, but they'll both spike up, and then this will come back down a little bit, but that'll never go higher than what it was. So they'll both spike up, and then they'll kind of do a little readjustment. We're not going to worry about that. That's a complex kind of reestablishment there. I should just remove that from the PowerPoint. We're just worried about the shift. Here, look at what have I got. O2 is they'll both be higher, slightly higher, but I don't even want you to worry about that type of thing. One last one. And then here's the plan. I'll give you some homework problems. I still have to talk about factors that don't affect an equilibrium system, what results in no shift. And I also have to teach you about how we actually can change some of these concentrations. And what we will do for that is, tomorrow at the beginning of class, I'll do the last part, how do we change the concentrations. Then we'll do the lab, and then at the end of class, I'll hopefully finish off that piece on factors that don't affect any shift. So in this case, we're increasing the volume of the container. So, pulling on the syringe. Spread those particles out. System is saying, whoa, they're spreading the particles out. It's way too thin. The response is, if you decrease the pressure and the concentration, the response is to increase the pressure. How is it going to increase the pressure? It wants more gas particles. Which side has the most gas particles in this particular one? Yep, Christian? The left. There's 3 gas molecules versus 2 gas molecules. I'm looking at the coefficients. This is going to shift left to produce more gas particles. All right? We'll stop there in terms of the note. I'm going to just jump ahead to some problems that you can look at. They'll just be qualitative problems, right? There's no calculations involved in this stuff. That's just a little picture of it, showing you how it squeezes it together. I'm not worried about that. We're not going to do that either. I still have to talk about factors that do not affect equilibrium positions. As you can see there, adding a catalyst doesn't affect it, but we'll write that down later. Also, adding an inert gas or a noble gas doesn't affect it. We'll start tomorrow's lesson by talking about how we can actually change reactants in products, all right? Because that's going to be everything about our experiment. And there are a few practice problems that go with this, and there's not many. And I really need you to print a copy of that lab for tomorrow, all right? The first page is the hypothesis. So what will happen is, after I talk about how we can affect the concentrations, which is what we have to do practically in the lab, you and your partner will sit down and discuss the hypothesis. You could actually do that tonight if you have it printed off. Well, actually, no, you can't, because you don't know how the changing of those concentrations are going to work. so you and your partner can sit down and then do the hypothesis. In other words, it's just left, right, what's going to happen to the color and all this other thing. And then you're going to do it, and you'll write down what you observed, and then there's just a handful of little questions on the bottom, you know, where your hypothesis is correct, et cetera, et cetera. Very straightforward. But I do need that printed off. Okay, that's a good place to end. I should put maybe the